Now this illustration deals with calculating the available short circuit current using a good rule of thumb method that electricians could use in the field. Even designing engineers can apply this method also. Back when I was a younger guy and in the field and also working for a firm, we used this concept because it's the only concept available to us. But notice the NEC loop. Let's talk about that for a moment. 110.9, it just says that all the terminals, the conductors and insulation and so forth, an electrical circuit or system should not be damaged if a short circuit or ground fault condition occurred. 110.10 was revised to basically allow the engineer or contractor, whoever had the authority by the state, county, or city to make this calculation, could start at the transformer, figure the available short circuit current there, size the conductors and the length of the conductors to limit the short circuit current to the point of delivery. And 110.10 just basically states that you could use anything of copper or any kind of resistance in conductors and so forth to limit the available short circuit current. And then 240.1, the informational note, says the overcurrent device should clear if it was on the load side. If you're not on the load side of the service and you're on the supply side, then it's the cutout switch that's ahead of your transformer on the primary side that usually will clear your fault. Now in our illustration, we have a transformer that's three-phase, 200 kVA, and 1.5 is the impedance of the transformer. The primary supply voltage is 13,800 volts. The secondary voltage is 48277, three-phase, four-wire system, terminating to a main in the switchgear. Now, the hazardous markings that should be on the equipment is in 110.16 A and B. And of course, you know the arc flash warning should be there, along with other warnings that are required that we have already talked about, 110.16. And 110.21B basically talks about this hazardous marking, either field marked or some of the markings may come from the manufacturer, then 110.16 would not apply. 110.25 deals where you had a disconnect or something up ahead that needed to be placed in the open position, locked and tagged out in accordance with NFPA 70E, Article 180, plus the Annex G of that standard, and also OSHA 1910.147. Now, the wiring method used is 4 250 kc mil THWN copper conductors. And with this information now, the note 1, we've already discussed that, whether either you're under the exception or you're applying the the 110.24 A and B, where the available short circuit current delivered starting at the transformer through the conductors to the point of delivery at the switchgear, as you see in the illustration. Now, method 1, to the left-hand side below, notice is 250 kc mil, and if we were using a C factor that was present in the old Busman handbook, it was a value of 16,487. If we were calculating the resistance of the wire using coated copper, then naturally we would go to the table 9, to chapter 9 in the NEC. Now notice the 250 kc mil conductors are routed in metal conduit. So that is where we would obtain the 250 kc mil THWN copper conductors routed in metal conduit. We would go to the table 9. We would look at that table 9 in chapter 9 to the NEC, and we would select the resistance based upon 250 kc mil size conductors, THWN, routed through metal conduit. Now, in our next illustration, we're going to review how this calculation is performed.